Let's look at this function here. This is an explicit function of y defined explicitly in terms of x. And I want to differentiate it. So when we differentiate it, we know we go dy by dx. You've probably just been told that by your teacher. You do dy by dx. This one disappears because it's a constant and we get 2x. Very straightforward. But what I want to consider is laying the ground rules for implicit differentiation. And I want you to think, why does that come as it does? Well, the reason for that is I want to differentiate every single term with respect to x. But y is a variable, so y changes as x changes. Now, when I do dx 4, that will not change with respect to x, so that's going to disappear. And this one's quite an easy one to differentiate. Now, this seems very long-winded, but what we're actually going to do is we're going to differentiate the right-hand side again. That disappears, and this becomes 2x, just like we had above. But what's interesting is how we get from here to here. And for that, we use the chain rule. So we're doing dy, and I'm going to put that over dy. And I'm going to times it by dy by dx. Now, what actually happens when this is saying differentiate y with respect to y, and that comes out as 1. And so it leaves on this side just a dy by dx. You can see there that they're going to cancel off, and that's just the chain rule. So that's why we have dy over dx is equal to 2x. Now you're thinking, so what? I was just told that. But that happens to be the real ground rule for doing a function like this, which is implicit. Y is not defined explicitly in terms of x. Now, if you want to know what this function looks like, well, I say a function, it's actually a relationship. It looks like this, it's a circle. And it's quite difficult to find, to differentiate it, to find variables. Because if we were to say, right, when x is 1, which is around about here, we have a point there on the line 1, and we have a gradient. Let me see if I can get a writing on here. So we've got a 1 here, and we're looking for the gradient here. We've also got 1 giving us a gradient here. So we've got 2 different y terms here. We've got a gradient there, and a gradient there. So it's not explicit which x number we're looking for. And this has an impact on differentiation. So what I'm going to do, I'm going to use what I did before to differentiate everything up here. So I'm going to differentiate x squared with respect to x. I'm going to differentiate y squared with respect to x. And I'm going to differentiate the constant term 4 with respect to x. Now this one, straightforward. Now this one, let's rewrite this as dy squared over dy, just like we did before, and multiply it by dy by dx. And when we differentiate this one, it gives us 0. So this is going to give me 2x. I'm going to differentiate y with respect to y, so we get 2y dy by dx equal to 0. And now let's rearrange that. So we have dy by dx is equal to, I'm going to take away 2x from both sides. I'm going to divide both sides by 2y, which of course gives negative x over y. So when I want to find a gradient in terms of x here as 1, I will also need the y number. And this is the gradient, or the rate of change of y with respect, sorry, of x with respect to y with respect to x. This is going to form the basis for all the work you do on implicit differentiation.